show you what will be covered today. In the past, we introduced 4 different kinds of optimization process. First kind is Newton's method. This is a 1D Newton. 1D Newton. Okay, someone said they don't have camera. It's okay, you don't need to show me yourself. You don't need to show me yourself. I just need to make sure you're here. No, don't worry. Okay, so let me get back. 1D Newton. This is the flow chart, how we could use Newton's method to find the minimum point when there is only one variable. So we call 1D Newton. I'm going to show you how to use Matlab to do this today. And secondly, we also introduce multi-dimensional Newton. So if we have more than one variable, we have a lot of variables, then we could use this flow process to find the minimum point. Okay, it's a multi-dimensional Newton. And after multi-dimensional Newton, we introduce a different method called steepest descent. Steepest descent, the purpose of steepest descent is to avoid using Bayesian, because Bayesian matrix is having a lot of second order derivative, and sometimes it's time consuming, and also avoiding the inverse of Bayesian. Steepest descent doesn't require the calculation of Bayesian and inverse of Bayesian. However, in steepest descent, we need to determine a new parameter called alpha, also called the step size, how far we move from the current point along negative gradient direction. How far is our movement in order to find the new solution? So to determine this alpha, we need to solve a sub-problem. That is like a secondary optimization process to determine how far we move along negative gradient direction. Okay, and lastly, we introduce a different method called conjugate gradient. In steepest descent, we know it doesn't move very fast. The iteration is slow, and conjugate gradient have a update of your moving direction. So when we update the moving direction by conjugate gradient, okay, so please mute. Okay, so if we update the moving direction by this, we should be able to move along a better direction, which is closer to our new solution. So we have shown that in the past. If you want to review how this method was derived, you need to check the lecture notes and video from last week. Today, I'm not going to derive any equation. I'm going to show you how these methods can be implemented in Matlab. So let's start. If you are a student from Taiwan Tech, I know our school has campus license for Matlab. So you could actually use your student ID to I think get the license for Matlab. So you can give it a try. Now let's start. This is Matlab. Let me start a new script. So I already did. And let me start with 1D Newton. And let me give some initial code. So usually I will say clear CLC and close all. What does those mean? Clear means clearing the memory space for variables. CLC is like clearing the command window here. And close all is to close all the figures that you generated. Okay, so this is usually what I would like to do at the beginning to make every code clean. And for 1D Newton, of course, at the beginning, we need to formulate our problem. So in this entire code, we need to do several things. We need to provide, to formulate the problem, formulation. And then we usually have initial setting, and then like an initial guess, and define some parameters. Then we usually need to do so-called sensitivity analysis. So what does sensitivity analysis mean? That means we try to evaluate the gradient. Like in almost every part of this, all the methods that we introduce, first we need to calculate some of the derivative. And in optimization, we usually call sensitivity analysis. So we need to do that. And then we need to do our iteration. Okay. And finally, we will, actually within the iteration, we should have our convergence check. And when we are done, we will show results. Actually, we will show results during the process. We will keep showing all the results during the process. So I'm not going to, there's no specific part for this one. So pretty much the entire code is like this. We formulate a problem, we define some initial setting, we perform a sensitivity analysis, we keep on doing iteration. At the end of the iteration, we need to do a convergence check. Until it's converged, we got a solution. And if you go back to every flow, it's always like this. Initial sensitivity. And this is the iteration. We iterate. And at the bottom of the iteration, we always have a convergence check. Only if we satisfy the termination criteria, then we can finish. So this one, I'm going to do 1D Newton. Let's see how we can start. So we need to formulate a problem. The Matlab is very convenient. We can use one way of programming is called the symbolic. Let me just, let me call it now. So sims represent defining a variable, a symbolic variable. So when a variable is symbolic, you can easily use several functions to evaluate the value. So let me show you an example. If I say sims x1 and say y equals to 2 times x1. And you can tell from the working space, x1 is a symbolic type of variable, and the y function is also becoming a symbolic type. And if you say substitute, subs means substitute, y, x1, and 2. So basically, it's like a plug-in. So when I plug in x1 as 2 into the y function, I get a result of 4. So this is a very easy way for you to substitute. And you can easily do derivative, diffy, x1, then 2x1 derivative with respect to x1 equals to 2. So that's how you can quickly compute derivative. So let's get back. First I generate this, I define this variable, and also I define a function. So let me call all my function as f. So now I say f equals to x1 squared. Okay. Now initial setting. So usually, of course, we know what's the minimum of x1 squared. It's basically 0, but computer doesn't know, so we can only make a guess. So let's start with a guess called let me use a different name. So I think the sigbar, yeah, let me call v1 the value of x1. So maybe I say v1. Is it confusing? Maybe x1 and v that represent the value of x1. Okay, and I will be keep recording every the x value in every iteration. So let me say iteration number k equals to starting from 1. If you are programming in C++, the index starts with 0, but in Matlab, all the index starts with 1. And that's why we usually we like to, so it will be a little different from what we introduced. Like we usually start with 0 right here, but sometimes that will cause some problem in Matlab. You make some mistakes with index. That's why in Matlab, I always like to start with not 0, but 1. So let me say like this, the value of x1 equals to some number, let's say 5. So that's my initial setting, just like this. I define an initial guess, and then the index is starting from 1. Now I need to do sensitivity analysis. So let me call df as the derivative. So diff f and x1. This is basically performing derivative. Well, let's see what will happen if we do this. The good thing about Matlab is that you can always just copy certain script in the command window and then just enter to show, to see what's going on. And what's the result of df? The x1 squared, derivative of x1 squared equals to 2x1. So the result of df is still a symbolic format. So it's very convenient for to use Matlab because everything is just like solving math. So let me get back. So now we know, okay, this gives me the symbolic form of first order derivative. How about if I do DDF? Let me use DDF to represent second order derivative. So basically you do another derivative with respect to x1 again, but this time you do it on df. So this is how you get second order derivative. Okay, now I need to actually iterate, and because we have a convergence check at the end, so I need to define some value that is to check whether the difference is small enough. So let me call the difference error. And let me just give it some initial number, which is quite large at the beginning. So my iteration won't stop when I see this value is large. Okay, this is like an initial value. It doesn't mean anything. And now for the iteration, I need to do a loop. So I will use, I like to use while loop. So while this error value is larger than 10 to the negative 3, I need to do iteration. And only if this value becomes small, then I get out. Okay, so now I'm inside the iteration. So first of all, we need to compute the derivative. So let me just call dfv as the value of the first order derivative. So df is the symbolic form, and dash underline v is the one when we plug in a value. So here basically you substitute, subs means substitute. You substitute into df, and you basically plug in x1, and then using the current value should be this one. You basically plug in the current value into the symbolic form of df. And this one right here, we do the same thing for the ddf. But here should be the value part. But I need to double check what's the result of this. So let me, DDF is symbolic. Okay. Question? Anyone has question? Okay, no question. Mute. Okay. So let me get back. I just double checked when I do derivative, even though, hold on. Please mute yourself, otherwise I hear echo. If when you unmute and creates a lot of echo, then you can type to me. There is a function, the chatting function. You can chat. You can chat. Okay, you can chat here. I can chat to everyone. Okay. You can message here. Okay, there's a message function if you would like to, if you have a question. Okay, I will continue. Now, like I said, I checked when we do derivative of f, the result is also symbolic. And if I do derivative again, it's also symbolic, even though it's the result is a number 2, but it's still in the symbolic form. So if you see DDF is a second order derivative. It looks like it's a number of 2, but it's actually like a character format. It's like a symbolic format. It's not a true value. So you need to evaluate it like df. Then it becomes a true numerical form. So this is how you need to get used to the programming in Matlab. Anyway, let's continue. So in the first part of my iteration, I basically plug in the current value. This is current value. And then I evaluate first order derivative and second order derivative. The results are here. So what would be next? Next, actually, I can write a note here. This is sensitivity analysis at the beginning of every iteration. So this is like a symbolic form of each derivative term. Okay, so now I need to implement 1D Newton's method. Oh, someone has a question? In the homework, blah, blah, blah. Okay. So let me answer some questions. Someone said, why do I say error equals to 100? Like I told you at the beginning, because this is my termination criteria. I wish this error becomes small, smaller than 10 to the negative 3. And this is how I decide if I want to stop. So here I just give some random number, 100, or you can just say 1 or any value which is larger than this. So you can give any number, it doesn't matter. Okay. And about the homework questions, maybe I answer later on. Okay. So let me continue to introduce my 1D Newton. So over here, you're supposed to write down the equation for Newton, for the Newton's method. So the equation should be the value of x1, but this time the index plus 1, will equals to the previous one, the current one, minus the first order derivative over the second order derivative. So that's it. This is how the Newton's method look like. You can take a look here. The current x minus first order derivative over second order derivative. And the result will be your next x. Okay? That easy. Now, actually, my convergence check should be written here. So here I update my error value. So the error value will be the absolute difference. ABS means absolute difference between what? Between the new solution and the previous solution. Okay, so that updates the error value. And over here, I need to advance my index value. So my k equals to k plus 1. Then this while loop will move back to the beginning. If this error value is small enough, then you will get out. Otherwise, you will perform a second round. And then in the second round, because my index value is advanced to a second second value, a second iteration. So these calculations will be recalculated. The derivatives will be recalculated at the new position. And this one will give me another round of new solution. So this process will keep doing it until it finish. So let me save this file and call this one 1D Newton. No underline, I guess. Just one denoting. Ah, don't do. You cannot start with a name. You cannot have the name that starts with a number. So let me call it Newton 1D. See. Okay. And then if I run it, actually it finished. And the solution, if you see this, actually the solution is initial gas, the solution in the first iteration, and then the second iteration. It looks like that, but you don't see anything. Now I'm going to show you how we could visualize the process. First, let's print out the text that indicates what happened. So every time we evaluate something, that's also, let's say, DISP means display. So we can display a string of characters. So over here, that means say iteration number equals to, so initially our value is K, yeah, so K, but K is double, it's a variable. So we need to, this function display only reads character. So we need to convert the value into character. So let's use number to string. This is number to string. That converts a number to string. So if I do this, what will happen? You will see a bunch of iter equals to 1, iter equals to 2, something like that. And let me continue. And let me put a comma there and a space. And oh, I also, let me do it later on. So let me just say x1 equals to some value. So what's the current value? Current value should be the new one. So I would like to show what's the value of the new one on the screen. And here I use number to string. Okay, let's see what will happen. So it's like, oh, iteration 1, I got a value of 0. Iteration 2, a 0 again. And I didn't show what's the initial. So let me do it here, just to display. So initially, of course, this is iterate. This is, let me say, initial guess. And over here should be this one. Run it. So here, I initial guess, x1 equals to 5. The first iteration, my solution equals to 0. And we can also show the value of error. If I want to show the value of error, I need to move this line to here. So I could, let me show everything after I got the value of error. So over here, because sometimes if you check how the error is minimizing, it is decreasing, then you can learn whether your coding is written correctly. Here, let me just number to string and the value of error. Sure. Here, so at the beginning, the difference between 0 and 5 is 5. So it's not yet converged. And now if my error, in the second iteration, the difference between 0 and 0 is 0. So it should converge. Okay, because this is a very simple problem. That's why it will converge very fast. Let's try to solve a different problem. Let's say I have a log x1 square. How does it look like? See, it takes, it explodes, sorry. It explodes. Let me see why. What does log x look like? Log x squared. Suppose we maybe the derivative is log. It goes to the other way. So what if I do this? No. Let me solve this. What about this one? Maybe this one has a solution. Okay. So very quick. No, it's not good because in the process, it actually gives an imaginary number. So not a good problem because log sometimes difficult to deal with. Let's try exponential function. Exponential function looks like this. If I do an exponential of x and then square, so how does it look like? Well, okay, this. Okay, let's try a function like this. Exponential x1 squared. Oh, it converges at iteration 22nd. So why does it moving so slow? Because the exponential function is having a very nonlinear slope. So Newton's method is based on a second order approximation, and the curvature of second order Taylor expansion is not nonlinear enough. That's why it won't converge very fast. It takes a while. Okay, cool. So at least we can see some results in text, but can we see this in graph? So let me show you how we can see this in graph. Here we can create a figure. And then let's say easy plot and the function f. And let me call zone. Zone means where I would like to plot this. Let me do plotting here. And the zone, let me define as 0 to 6. Let me plot out the region between 0 and 6. Easy plot. It's fine. Let's say hold on. Hold on means you can plot something else on top of the same figure. Let's see what will happen. It's iterating, so I should use another command to, yeah, it plots out this. But here, if I say draw now, that means you don't complete all the calculation, then draw. You should draw the figure right away. Okay. So you do it again. We'll plot, then continue to do this long calculation. I think this is taking too long. Let me start with easier initial guess. Let's start with 2. Then plot out the region from 0 to 3. It's a shorter process, 9 iterations. Okay, cool. Now I just plot out the function, and if you feel like the curve is too thin, you can make it thicker. Let me show you how to do it. You can say h equals to this, and in Matlab, when you plot out something, you can actually it's a object-oriented programming. So the figure is an object, and you can uh, every object has a number in Matlab. So you can say h equals to some process, and if it generates some uh, number, some value to represent the object, then it will just return to this variable you just defined. So h we call the handle. When we say handle means the variable to that give you access to that object. So over here I can say set h and say line width and 2. Let's see what will happen. No. Oh yes, it become a thicker line, right? A thicker line. Now, also when I plot this, I feel like the font size and the background of the figure is not the style that I like. So usually I will say set. Let me show you what I usually do. GCF and color, and I will explain later white. And set GCA. Font size 15. I think that's enough. Let me run it first, and I will explain what. Okay. GCF is the. Let's see. From my expression. Let me mute. Okay. So GCF is the handle of that figure object, the entire window. And GCA is the handle for the axis. This for every plot you made, it's called axis inside Matlab. So when you say GCF or GCA, that means you are trying to specify something to the object of the figure itself, or the axis. And then when I say set GCF color white, that means I convert the background color of the figure to white. And when I say GCA and change the font size to 15, then I have a larger font size that is, which is more readable. And the reason why I do these is just because I can directly take this for papers. So if you can print, if you can print the figures in a nice format, you can directly use it for papers. So let me also share some of my experiences. Someone just suggested I could try initial guess of 1, because that shows. Actually, I think 2 is fine. 2 is fine. Now, I would like to plot out where is the position of my variable. So to do that, I will need to say plot and the xy coordinate of the point. So for the x coordinate, I'm going to set the current x here. And for the y coordinate, I actually need to plug in to get the value. So how do I plug in? Substitute and f, x1, and then current value. So that tells the computer this is my X point, this is my Y point, and then the style of the printing, I'm going to draw a circle, and about red color, and the marker size is around 8, and line width probably 2 again. Let's see. The draw now should be given here, so you see everything right away. Okay, so that's where our initial guess is. Let's plot the whole thing between 0 and maybe 2.1. So can you clearly see, okay, this is about 2.5. You can clearly see how the curvature of the function look like and where is the position of our initial guess. So we can do the same thing during the iteration. So let's continue to do this plotting whenever we get the new solution. So over here, the only difference is that you have the index is different. So +1. And yeah, that's pretty much what we need to run it. Sorry, I should say draw now here. So whenever a new value is calculated, it plot out right away. So you will see a animation like this. Okay, and if you are interested, you can actually zoom in to here. You can see how close the points are. How many points here? Sorry, I used the wrong function. I should use yeah, that's really is. Yeah. I think I was right. I just want to show you how close the points are. So this is 10 to the negative 8, very close to 1, but very close to 0, but not exactly 0. So there should be like, I think this is the point. This is the last point, okay? So this is how you can solve the problem, a 1D optimization problem. Okay, and if you change a function, let's change back to x1 squared. Let me do this. Oh, it's so fast because it's a second order problem. If I do a third order function, if it's a third order, because the order is higher, it's not second order. So Newton's method will make approximations at every design point in a second order way, and then move on to a new position. Okay, so this is 1D Newton